All right, there we go. I got everything set up. I have a little bit of a different setup today. Oh, shoot. What is that? Oh, no. I'm breaking the artifice already that I've created. Yeah, I have a green screen now. That's the thing. It's not very... my camera's not really that good at picking it up, though. So... we'll see how that works as we move on into the future, but right now I'm just gonna study a little bit more. Apparently AAMC has already announced the test dates for next year, and registration is happening on October, so time is running short and I am in great need of speeding this up and getting in more regular practice. So let's do this.
Is the site that the ribosome is going to recognize and bind to. So let's just do a ribosome right over here. This is where the prokaryotic ribosome is going to bind. And then after the Shine-Delgarno sequence, we have another non-coding region, just going to abbreviate it NCR, and then we have our start codon, which is typically AUG. So that tells us to start. And so the ribosome is going to start translating. It's going to read this entire section, put together the corresponding polypeptide chain until it hits the stop codon, which tells it to stop translating. And then we have another non-coding region. Let's look at our eukaryotic mRNA. And so it's pretty similar, but you can see there are some differences. So we'll start with our 5' side first. So you see this red nucleotide right over here. That's the 5' cap. And the 5' cap is simply a guanine nucleotide, so I'm going to draw a G inside, guanine, and it's going to have a methyl group somewhere on the molecule. So I'm going to draw a methyl group, and the bond between this guanine and the nucleotide right near it is a bond that's different than the bond you typically find between two nucleotides. And so that's really all the 5' cap is. And the 5' cap is actually the ribosomal
I'm just looking at my map right now,
so
and I'm seeing that
the ribosome is going to recognize
this only includes eukaryotic mRNA.
So after the 5' cap, we have this other non-coding region, which the ribosome is not going to translate. And then the ribosome is going to hit the start codon again, AUG. Tell it to start, and it's going to start translating. So it's going to translate this entire section until it hits the stop codon. And then we have another non-coding region. And then we hit something that looks different than what we've seen in the prokaryote.
Okay, what I'm going to do is... let's see, where can I put this? The Shine-Delgarno sequence is concerning me at the moment. Garno. I'd like to include that somewhere. I don't think it's going to be a big deal, but let's just put it over here. Assuming that my program works and doesn't break. Okay. Delgarno. 100% sure on what that is.
Delgarno sequence. And the Shine-Delgarno sequence is the site that the ribosome is going to recognize and bind to. So let's just throw a ribosome right over here.
I see. Okay. That is only for prokaryotic. It sounds like 5' cap. Does this... no, it does it do a similar thing to that? Oh, shoot. Okay. Let's put this here. Prokaryotic. Yeah. Prokaryotic right there. mRNA. Okay.
Here, this is where the prokaryotic ribosome is going to bind. And then after the Shine-Dalgarno sequence, we have another non-coding region, just an abbreviated NCR, and then we have, that means that in eukaryotes, the ribosome is going to recognize this particular part and bind to it.
Oh, I'm a genius.
So after the 5' cap, we have this
5'
other non-coding
cap
region,
is where you
which the ribosome is
recognize
not
the
going to
thing.
translate.
Nice.
And then the ribosome is going to hit the start codon again, AUG. It'll hit the start, and it's going to start translating. So it's going to translate this entire section until it hits the stop codon. And then we have another non-coding region. And then we hit something that looks different than what we've seen in the prokaryotic mRNA. So this section with blue nucleotides, and that's called the
Poly A
poly-A
tail. Got
And the
him.
poly-A tail is a bunch of nucleotides that are all A's or adenines. So I'm going to draw A's inside all of these nucleotides. And the poly-A tail is actually pretty long, so it's typically anywhere between 100 and 250 nucleotides long. So that's pretty long. So I didn't exactly draw it to scale. And the purpose of both the 5' cap and the poly-A tail is to prevent this mRNA from being degraded by enzymes. So it acts as this kind of signal that does not allow enzymes to break it down or degrade it. And so you might be wondering, well, what about prokaryotic mRNA? How come they don't have anything similar to prevent it from being degraded? And the brief answer to that question is that in prokaryotic cells, transcription, that's an R, and translation both happen in the same place. So prokaryotic cells don't exactly have a nucleus. They have this, like cytosol, and transcription and translation are happening in the same place. And not only are they happening...
Okay. I didn't realize that. Interesting. Okay. Karyotic mRNA. Kind of a tough line to draw here. To draw some kind of connection between translation and transcription in regards to RNA, or sorry, in regards to prokaryotic cells. It's kind of difficult, actually. Let's see. Line this up, bring this down. Okay, this soundtrack is going through all the sad music right now. Also, I don't even know where this is. Where is this coming from? That's weird. Oh, it's still on shuffle. Oops. Oh, well, in that case, I just got really unlucky. Let's switch to... go with our classic battle theme. Perfect. Okay. Prokaryotic mRNA needs to go here. Actually, I'm gonna just say prokaryotic. Prokaryotes. Prokaryotes. Gonna have a separate thing going on. I need to watch out for these arrows, because now I am making things very unreadable. Okay, this goes here. Transcription, translation. Same. I'll just stick with what they said. Same place for translation and transcription. Boom and boom. And then oh, Shine-Dalgarno. But see, this doesn't really make sense because I initially put the Shine-Dalgarno sequence there in reference to the prokaryotic mRNA, and now there's a line going from prokaryotes being in the same space Okay, you know what? Let's just make it easier for all of us and just cancel this out. Just say something about prokaryotes. Something about prokaryotes is important here. And then call it a day.
In the same place, but they can actually be happening at the same time. So you can have a piece of mRNA that's being formed, and while it's being formed, the ribosome will attach to it and begin to translate it. But in eukaryotic cells, things are a little bit different. So transcription happens in the nucleus, and translation happens in the cytoplasm, where there are ribosomes. And so the mRNA, after it's made, has to travel from the nucleus to the cytoplasm to where the ribosomes are. And so because it's traveling this relatively large distance, it's going to encounter a lot of different things, including enzymes that might break it down. And so it needs this extra protection to prevent it from being damaged in any way. There's one more difference I want to talk about in how translation happens in prokaryotes and eukaryotes, and that is what the first amino acid in the polypeptide chain will be. So in prokaryotic cells, the first amino acid in the chain is always formylmethionine. And formylmethionine is simply the amino acid methionine, but with a formal group attached, and in case you don't remember what a formal group looks like, it looks like that. In eukaryotic cells, the first amino acid in all the polypeptide chains is simply methionine. And it's interesting to note that formylmethionine actually acts as an alarm system in the human body. So if you have some bacterial cells in your body that are damaged anyway, there will be these formylmethinines floating around, and that tells your body that there are bacteria around and it's going to trigger an immune response.
Okay, so prokaryotes just feel like being a rebel, or maybe it's the eukaryotes that feel like messing up everything. So let's just have this kind of sticking somewhere around here. Maybe change up the information as well. Color of the lines. Let me go with the purple to signify that these two are related to the chain. Also known as the central dogma. So it's just going to travel around here. Shine Delgarno is important so that we can actually translate the mRNA, and the translated mRNA is going to result in FMET being the first amino acid added to the chain. So that makes sense. That's all good. Yeah, and then the black lines are just gonna be pointing out that those are connected somehow to prokaryotes. Perfect.
Let's take a look at a segment of DNA that's in the process of being replicated. And I want to focus in particular on the enzyme that replicates DNA. That enzyme is DNA polymerase. And actually, there are two different types of DNA polymerases, and one that we're looking at right now is DNA polymerase 3. So DNA polymerase 3 synthesizes new DNA, and it also has the ability to proofread.
Oh my god, why are the energy points on the thing? Okay, thank you.
Before we get into that, just order yourselves and quickly summarize the diagram that we're looking at. So this enzyme over here is DNA polymerase. That's the enzyme that unwinds the double-stranded DNA so that DNA polymerase can come in and start replicating. Right over here, you can see I drew the back in a different color. That's the RNA primer. Now let's just label the DNA strand that's being synthesized. It's synthesized from 5' to 3'. And actually, the bottom strand of DNA is synthesized at the same time as the top strand, but I just left that out of the joint to keep things simple. And let's say that the yellow bases represent the nitrogen-based thymine. Let's say that the orange bases represent cytosine. The green ones represent adenine. And the blue ones represent guanine. And so thymine and cytosine are the pyrimidines. They are composed of a single ring structure. So they're made up of one ring that has 6 sides to it. And then adenine and guanine are the purines. They are a double ring structure. So they're composed of one ring with 6 sides to it, and then that ring is attached to another ring that has 5 sides to it. And actually, these structures are a little bit more complex. There are other atoms, in it, and there's some double bonds, but we're just going to keep things simple for now and leave it at that. And so let's get back to our DNA that's being replicated. Right over here, I left a space. I didn't put the nucleotide. And let's say that by accident, instead of it being paired up with the proper base, which is adenine, it accidentally gets paired up with a guanine. So that's a mistake. And DNA polymerase 3 actually has the ability to sense if it made a mistake. And if it does realize that, it's going to go backwards, and it's going to actually remove the incorrect base and replace it with the correct base. So let's do that. It's going to remove the incorrect base and replace it with the correct one. Of course, remember the nitrogen base is attached to the sugar backbone. And so this activity that I just described to you is called exonuclease activity. And so nuclease tells us that means the ability to remove a nucleotide. And exo, just going to underline that. So exo tells us that it can remove a nucleotide, but only from the end of the DNA strand. So it was able to remove the nucleotide because it was at the end of the strand. This is in contrast to endonuclease activity. So an endonuclease can actually remove a nucleotide from the middle of a DNA strand. So it will be able to remove, I don't know, a nucleotide from like right over here, for example. And just keep that in mind because we're going to come across some endonucleases as well. Anyway, back to our exonuclease activity. If we want to be more specific, the exonuclease activity of DNA polymerase 3 is actually 3' to 5' exonuclease activity. And the reason it's called 3'.
These videos are so quiet. Okay.
When DNA polymerase 3 makes that correction, it has to move backwards in the 3' to 5' direction in order to do that. There's another enzyme, DNA polymerase 1, which is going to abbreviate polymerase with POL. And DNA polymerase 1 also has exonuclease activity. And DNA polymerase 1 is actually the enzyme that will remove the RNA primer at the end of replication. And just as a side fact, the exonuclease activity of DNA polymerase 1 is actually in the 5' to 3' direction. So if you that means the ability to remove a nucleotide, which is adenine, it accidentally gets paired up. They're composed of one ring with 6 sides to it, and then that are composed of a single ring. And the blue ones represent guanine. And let's say that let's just label A, and it also has the ability to proofread, or kind of.
Okay. So now we're talking about DNA repair, which I probably should have expected. Now that is the reason why I need to move things out of here and figure out where to put it. Technically speaking, we can put that separate from replication. Yeah, alright. We'll just make a new branch here. We know that DNA polymerase is necessary in replication as well, but I don't actually know which variation of the DNA polymerase that is being referenced over there. In any case, DNA repair, that can stay purple. That's pretty important to DNA actually functioning the way it does. So let's do this. Drop in a DNA polymerase 3. Oh. Going through all of the sound effects today. DNA polymerase 3 is the proofreader. Oh my god, I don't want that to be purple. Someone help me. Okay, there we go. Okay. The problem with these mind maps is that as soon as you have too many things on the map, you'll start accidentally connecting random stuff that's not supposed to be connecting. Because there's a limited way of telling the program what command you want to do. Alright.
The DNA is putting together, make sure that they're size from 5'. They are a double ring structure. So they're composed of one ring with 6 sides to it, and then that ring is attached to another ring that has 5 sides to it. And actually, these structures are a little bit more complex. There are other atoms, in it, and there's some double bonds, but we're just going to keep things simple for now and leave it at that. And so let's get back to our DNA that's being replicated. Right over here, I left a space. I didn't put the nucleotide. And then let's say that by accident, instead of it being paired up with the proper base, which is adenine, it accidentally gets paired up with a guanine. So that's a mistake. And DNA polymerase 3 actually has the ability to sense if it made a mistake. And if it does realize that, it's going to go backwards, and it's going to actually remove the incorrect base and replace it with the correct base. So let's do that. It's going to remove the incorrect base and replace it with the correct one. Of course, remember the nitrogen base is attached to the sugar backbone. And so this activity that I just described to you is called exonuclease activity. And so nuclease tells us that means the ability to remove a nucleotide. And exo, just going to underline that. So exo tells us that it can remove a nucleotide, but only from the end of a DNA strand. So it was able to remove
oh
the
my
nucleotide from the end of the
goodness,
strand.
it's doing it
This is
again.
in contrast
Alright.
to endonuclease activity.
So
So an endonuclease can actually remove
activity.
a nucleotide from the middle of a DNA strand. So it would be able to remove, I don't know, a nucleotide from like right over here, for example. And just keep that in mind because we're going to come across some endonucleases as well. Anyway, back to our exonuclease activity. If we want to be more specific, the exonuclease activity of DNA polymerase 3 is actually 3'
Alright,
to 5'.
my logic tree is not working here. Hold up. This is wrong. This needs to be exonuclease activity, which is a form of proofreading. So it goes that direction, and then proofreading also goes down in referencing endonuclease activity to catch problems happening in the middle of the thing. Endonuclease. I think I'm pretty sure I wrote that correctly. Thanks. Endonuclease activity. Oh boy, okay. That looks pretty good. I'm a
The reason it's
genius.
called 3' to 5' exonuclease activity is
3'
because
to
when
5',
DNA polymerase 3 makes that correction, it has to
yeah.
move backwards in the 3' to 5' direction in order to do that. There's another enzyme, DNA polymerase 1, I'm just going to abbreviate polymerase with POL. And DNA polymerase 1 also has exonuclease activity. And DNA polymerase 1 is actually the enzyme that will remove the RNA primer at the end of replication. And just as a side fact, the exonuclease activity of DNA polymerase 1 is actually in the 5' to 3' direction. So if you want, you just keep that in mind. And so DNA polymerase 3 and DNA polymerase 1 are both able to repair or fix mistakes that happen during DNA replication. And just to give you some perspective as to how often this occurs with and without repair.
Okay,
So,
wait, now I'm dumb. Okay, hold up. Let's move this over here, actually, so that we can include DNA polymerase 1 in this, three-way relationship with exonuclease activity. Look at that. Amazing. One's gonna be over here. And go ahead and poke. Exonuclease activity. And there you go. Alright. With that, the only problem left over is the direction that I need to specify here, which can be 5', 2, 3', in the sense that it's going to go ahead and pull back and try and grab the RNA primer. This is 3', 5'. Yeah, to catch mistakes on the God damn it, what is it called again? The new strand. The one that is being built off of the template strand. It's literally just called the new strand. Am I missing something here? Case leading strand. Replicated strand? Whatever. It's the new strand. Three to 5'. To fix mistakes. Own mistakes. Gotta respect DNA polymerase 3 for fixing its own mistakes. Takes a lot of guts to do that. Respect. Alright, nice.
normally we'll have a mistake happening in replication between 1 in 100,000 bases to 1 in 1 million bases. So let's just say that this strand over here is the same as that strand. Let's say that the bottom strand in our original DNA is the same as this strand. And so let's look first at the newly replicated DNA on the left. So we have right over here a thymine base, and assuming DNA was replicated properly, it's going to have an adenine complementary to it. Now let's take a look at the DNA on the right. So on the bottom we had a guanine, and it's going to be paired up, hopefully with the correct base, which is a cytosine. Now let's just quickly look back at our original DNA. We were supposed to have a thymine with this complementary adenine. And actually, that's exactly what we got over here. Just gonna circle it.
Okay.
So this DNA is actually the correct sequence. But look at the DNA over here on the right. This is not correct. This is a mutation. And this is an example of how mutations can occur if the DNA repair mechanisms are not working properly. And so let's go back to our original question. Can we fix the original mistake so that this mutation does not occur? And the answer to that question is yes. So fortunately, our cells have what's called the mismatch repair mechanism. And the mismatch repair mechanism is composed of a number of proteins. And the first thing these proteins are going to do is they're going to recognize if there's a problem. And the reason that they're able to recognize the problem is that when you have a mismatch in DNA, it tends to distort the sugar backbone a little bit. And they're going to mark the area with a cut. So they're going to cut the incorrect base, or mark it with a cut. The next thing that's going to happen is an exonuclease is going to remove the incorrect nucleotide. So we're going to remove the incorrect nucleotide. The next step is one of the DNA polymerases is going to insert the correct nucleotide. So we're going to pair our thymine up with adenine. And the last step is a DNA ligase is going to connect the new nucleotide to the nucleotide
Oh
on
my
its
god,
sides,
this is 2 times
and
speed.
also to its complementary nucleotide on the other strand. And I'm actually going to just correct that distorted sugar backbone. And so
That
here's
seems
our
so slow.
repaired DNA. And just to clarify, the mismatch repair mechanism that we're talking about here happens after replication. The repair is done by DNA polymerase 3 and DNA polymerase 1 that we discussed before. That happens during replication or at the end of replication. And so one thing you might be wondering is, how does the mismatch repair mechanism know to distinguish between the original parental strand and the newly synthesized strand that has the mistake on it? In other words, how does it know which base over here is correct? In our case, that's the thymine, and which one is incorrect? In our case, well, it was guanine. And we know the answer to that question in bacteria. So in bacteria, the parental strand will have adenines that are methylated. So I'm just going to draw some methyl groups on all the adenines. And that allows the mismatch repair mechanism to kind of recognize and distinguish between the original strand that has the correct base on it and the new strand that has the incorrect base on it. But we're not quite sure how the mismatch repair mechanism in eukaryotic cells and in other prokaryotic cells knows to distinguish between the strand that has the correct nucleotide and the strand that has the incorrect nucleotide.
That's interesting. All right. Wait, actually, I do want to go back and listen to that explanation with the
There are certain things
methylated
that can cause
adenines again, because that is weird but interesting. It helps you identify which strand exactly?
One thing you might be wondering is, how does the mismatch repair mechanism know to distinguish between the original parental strand and the newly synthesized strand that has the mistake on it? In other words, how does it know which base over here is correct? In our case, that's the thymine, and which one is incorrect? In our case, well, it was guanine. And we know the answer to that question in bacteria. So in bacteria, the parental strand will have adenines that are methylated. So I'm just going to draw some methyl groups on all the adenines.
Okay.
And that allows the mismatch repair mechanism to kind of recognize and distinguish between the original strand bacteria, and which
parental strand will have
adenines that are methylated. So I'm just going to draw some methyl groups on all the adenines. And that allows the mismatch repair mechanism to kind of recognize and distinguish between the original strand that has the correct base on it and the new strand that has the incorrect base on it. But we're not quite sure how the mismatch repair mechanism in eukaryotic cells and in other prokaryotic cells knows to distinguish between the strand that has the correct nucleotide and the strand that has the incorrect nucleotide.
Okay, I don't know if we need to memorize that because that's only bacteria only. And I guess they just like mark the parental strands before they have to get replicated and then repaired later.
There are two thymine bases that are kind of stuck together, and that's called a pyrimidine dimer. So a dimer is simply when you have two molecules that are identical, they're stuck to each other, and pyrimidine tells us that it
Okay, hold up.
cause damage to the structure of DNA. And one example of that is UV rays. And so before we get into the damage that UV rays cause, let's just focus for a second on the key that I drew here on the left. Bases are kind of stuck together, and that's called a pyrimidine dimer. So a dimer is simply when you have two molecules that are identical, they're stuck to each other, and pyrimidine tells us that it can be two thymines that are stuck together, or it can be two cytosines that are stuck together. And UV rays cause the formation of pyrimidine dimers. And so you can see that the pyrimidine dimer actually is causing the sugar phosphate backbone to protrude or kind of stick outwards. And not just that, but because the backbone is sticking outwards, the bond between this cytosine and this guanine snapped. So you can see that there's some structural damage that happened to the DNA. And so what are some factors that can cause damage to DNA? And I want to just make a clear distinction between a mutation and DNA damage. So it's not the same thing. A mutation is when you have a change in the sequence of DNA. So for example, if we had a piece of DNA that read A, T, C, G, and then something happened and it read A, C, G. So this A is in the wrong place. That is a mutation. But when we talk about DNA damage, we're talking about damage to the structure of DNA, but the nucleotides are actually in the correct order. And so DNA damage can be caused by endogenous or internal factors, and that means factors that originate within us, within our own cells. So for example, there are certain byproducts of metabolism that can cause DNA damage. Or DNA damage can be caused by exogenous or external factors, and those are factors that originate outside of us or outside of the organism that we're discussing. So let's start with exogenous factors first. So we spoke about one of them, UV rays. And there are a lot of exogenous factors that cause DNA damage, but we're just going to list a few. Gamma rays can cause DNA damage, X-rays, and so that's why it's not healthy to be exposed to a lot of these rays. And now let's talk about some endogenous factors. So reactive oxygen species is an example of an internal factor that can cause DNA damage. And reactive oxygen species are molecules that contain oxygen, and they're highly, highly reactive. So there are a lot of different kinds of reactive oxygen species, but we're just going to give two examples. So for example, a superoxide anion, which is O2 with a negative charge. So let's just draw that. It's two oxygen atoms that are bound together, but there is one extra electron. And I'm actually going to draw the extra electron in a different shade, of purple. And so this whole molecule has a negative charge. So that's a reactive oxygen species. Another example would be peroxides. So peroxides are molecules that have two oxygens, and on either end there's another atom. So that R can represent the different, different types of atoms. So this is the general way that a peroxide looks. You might have heard of hydrogen peroxide. So this is hydrogen peroxide. And so where are these reactive oxygen species in our cells coming from? So actually, reactive oxygen species are a normal byproduct of the electron transport chain in the mitochondria. So there are a lot of reactive oxygen species all over our cells. But fortunately, we have many enzymes that help protect against the damaging effects of reactive oxygen species. And you may have heard of the term antioxidant. And so an antioxidant is a molecule that also helps protect us against the damaging effect of reactive oxygen species. You may have heard that certain foods are really healthy because they have a lot of antioxidants, and that's true. So vitamin C, for example, is an antioxidant. Vitamin E, and there are many different types of antioxidants, but we're just going to give these two as an example.
Take your antioxidants.
And so now that we've discussed some of the sources of DNA damage, let's go back to our damaged DNA and see if there's a way to fix this. So our cells can get rid of these pyrimidine dimers in a process called nucleotide excision repair. And so the first step in nucleotide excision repair is an enzyme, an endonuclease, is going to remove the pyrimidine dimers and any other nucleotides that are kind of not the way they're supposed to be. And so I just want to pause for a second and analyze that word. So nuclease tells us that it's an enzyme that's able to cut out nucleotides, and that prefix endo tells us that it's able to cut out nucleotides from within a DNA molecule. That's in contrast to an exonuclease that can only take out nucleotides that are at the beginning or end of the DNA molecule. But anyway, the endonuclease is going to cut out the dimer and any other nucleotides that are not properly arranged. So let's just cut out all these nucleotides. The next step is a DNA polymerase. I'm just going to abbreviate that POL, is going to come and bring the nucleotides that belong there. And the last step is DNA ligase, is going to make sure that those new nucleotides are attached properly to the nucleotides on either side.
I don't know if my mic is catching that, but there are currently rumbling cars outside my apartment, and it is loud. Can't even hear whatever is coming out of these headphones I got. In any case, I'm still kind of behind. I'm just trying to catch up. Nucleotide excision repair is very cool, but I want to quickly note down superoxide and peroxides. Just because I can, really. Sounds like someone's street racing out there, goddamn. I want to watch. Oh well. So it's alright, nice. Yeah, that's hot. Alright. It's looking pretty good. Oh, wait a minute. Wait. Oh, shit. There we go. Not really. Ah. Misalignment is killing me. I hate that so much. Once this is all over, I'm just gonna spend an entire, like, day just, like, realigning everything. Let's not worry about that too much right now, though. Alright, and then this is the nucleotide excision thing. Mismatch repair does not need to be purple. Gotta have some standards for the purple path of central dogma. Nucleotide excision thing. What is it called again? Repair. Oh, of course it's called repair.
It's going to come and bring the nucleotides that belong there. And the last step is DNA ligase. It's going to make sure that those new nucleotides are attached properly to the nucleotides on either side, and also to the nucleotide that's complementary on the other strand. And so that was a mouthful. Let's actually just draw all of that. So let's get rid of our backbone that's kind of protruding and just not right. So let's redraw our backbone, something like that, or actually a little close there. And then DNA polymerase brings the correct nucleotides, but remember it's the ligase that actually connects the nucleotides properly. And so here's our corrected DNA. But what happens if for some reason the nucleotide excision repair is not working properly? And this repair mechanism is only one example. There are many different types of DNA damage that can occur, and many different types of repair mechanisms. What happens if for some reason one of these or a couple of these are not working properly? Then we get a cell that has a lot of damaged DNA. And there are three things that can happen to a cell like this. The first is it might go into this dormant state where it just ages and does not divide anymore. That's called senescence. The second thing that might happen to it is what's called programmed cell death, or apoptosis. And that basically means that the cell's going to commit suicide and die.
Oh yeah, senescent cells. I've heard about that. Oh shit. Yeah, that's the big buzzword around a lot of bioengineering companies. They're like, oh my god, senescent cells. Yeah, so a bunch of cells just kind of like decide not to do anything anymore. And they're like, well, shit, we have so many useless cells now in the like older, like as your body gets older, you start accumulating all these cells that just don't do shit. And it's like, bro, this is not helpful. This is why we get worse as we age. I guess all those companies are trying to solve immortality. Very epic. Apoptosis, senescence. Of course, the whole point of healthcare is to prolong life. So, I'm just making jokes because it seems like such a difficult problem to begin with. Damn. We're really going at it. Very curious what that's going to look like in the future. But for right now, I haven't really heard too much about senescence past that kind of like initial hype. Gotta wait before you pre-order the game, you know?
Unregulated cell division.
Unregulated cell division, that's
And
cancer.
this was cancer.
Yo!
And so actually the skin cancer melanoma is an example of this. Melanoma, that's an N. Melanoma happens when the nucleotide excision repair mechanism that we just discussed is not working properly. And so you have this accumulation of pyrimidine dimers that damages the DNA very much, and then the cell starts to divide uncontrollably.
Yep. Cancer, or... Did I explain it in the way that they did? I don't think so. Oh my god, just... Take me back.
Melanoma.
Unregulated, and no, I'll just call it cancer. That's what it is. We know what it is. It's terrible. And we need to figure out how the hell to make some changes. I've heard good things about researching cancer, so sounds like we're working on that real quickly. I don't know exactly what happened. I'm blanking on it right now.
Let's take a piece of DNA, and let's just unwind it into its two strands, and just help us remember that DNA is really a very, very long molecule. I'm going to put arrows here on our two strands of DNA. And the question I want to ask you is, if we were to replicate this DNA, what would the end result look like? We have our old pair of DNA, and then we synthesize a completely new pair represented in blue. Replication, we're going to end up with two pairs of DNA, double strand. You're in this kind of neat ratio, or vice versa. Each pair has one old strand. Scientists, one by the name of Meselson and one by the name of Stahl, and they conducted a famous experiment which was named after them. So the Meselson-Stahl experiment. And in this experiment, they proved that DNA replication is semi-conservative. So this is how DNA is
What is the point? Okay. Sure. I mean, yes, that's an important concept, but alright. Semi-conservative. Are we just here to talk about the guys who figure that out? Which I am cool with. I'm totally down to respect
This is how DNA.
the history of science, so let's go ahead and drop a like and subscribe for Helselson and Stahl. Boom. I need to come up with more color codes as well. This is looking kind of stale. Alright. Where were we? Random side bit, but that's cool. Protein modifications. Okay. Now this is exciting.
After a polypeptide chain is formed, it's going to be folded into its secondary and tertiary structure into a very specific 3D conformation.
Oh my god, it's so
shape.
quiet.
And at this
Why
point,
is
we can
this so
start calling
quiet?
it a protein. But this protein may not be ready to carry out its function just yet. There might be some additional protein modifications that need to be made to this protein before it can be functional. And those are called protein modifications. There are two different types of protein modifications. The first type is co-translational modification. And that means that these are modifications or changes that happen to the protein, or actually to the polypeptide while it's being translated. So
Wait,
with the ribosome
what
right
is-
here and
what is
the
the one thing?
polypeptide.
Oh yeah,
being
enzymes
formed.
are
So
over here.
these changes are going to happen while the polypeptide is being formed.
Oh
And
my
an example
goodness.
of a co-translational
Oh,
modification
no.
is acetylation.
Oh god.
And
I
what happens during
can't find
acetylation
where
is
my
the
stuff
first
is.
amino acid in the polypeptide, which is usually methionine, is going to be removed. And in its place, we put in acetyl group. So let's just draw an acetyl group. And acetylation happens to 80 to 90% of eukaryotic proteins.
I mean,
But
we
have
could move
significant
enzymes
not
all the way
very
up
well
here
after
and
trying
put
to
it like
figure out what the purpose of this modification is.
here,
The other type of
but
protein
like
modification that happens is
let's not.
post-translational modification.
I'll deal with that later.
And actually, most protein modifications fall into this category, and the examples we're going to discuss in this video are all post-translational modifications, and those modifications happen after translation. Many post-translational modifications happen in the endoplasmic reticulum and the Golgi apparatus, but not all of them. So let's go through some examples.
Cool,
So the first
cool.
post-translational
Very
modification I want to talk about is
awesome.
glycosylation.
Right now,
And
I'm trying to
glycosylation,
find
well, you know
space
the
for
word,
this
the
thing.
prefix glyco tells us that it has something to do with a carbohydrate. And so glycosylation is the adding of a carbohydrate to a protein. And most of the proteins in this video are on green. And glycosylation usually happens to proteins that end up being embedded in the cell membrane. So you can see here we have a cell membrane, and there's protein embedded in it, and then there are these carbohydrate groups attached. So here's a carbohydrate group attached, and here's another one. And glycosylation helps to identify different types of cells. And one very common example of
Whoa! I request you to chill. Oh my goodness.
Acetylation to 90%.
I know I have you at 2x speed, but like still. God damn. Oh wait.
So the first,
whoa.
but not all of them.
All right, code translational. Oh wait, no, protein modifications. Man, mind map is already big enough to be like lagging like this. This is not good. Elation. I wonder what premium on this website would look like for me, aside from letting me make more than just 2 mind maps. Ugh. The limits. I mean, it doesn't even matter in this case because I want to like have it all in one for the MCAT, but you asking a bit much for their servers. Post translational. Okay. All right, we'll pick up later because I got another stream to get to. So I'll see y'all later, and good luck on your studies.